Okay, welcome back, and welcome back to section 1, and this is part 2, which will go about 15 or 16 slides or so. And we'll cover the remainder of section 1. Most of part 1 was simply just getting oriented with the narration process. Otherwise, I'm going to activate the laser pointer so I have it just in case I need it. And let's move on. There's nothing to do with the student learning map at this point. We'll revisit the student learning map and when we get to section 2, which will be in a different video. Okay, here's the last slide that we left off with, and this is the first slide that we want to start. Let me get the whole slide up. Okay. Pure substances. Remember that we're discussing matter, and matter can be subdivided into two different classifications. We can have a physical mixture and we can have a pure substance. We're going to talk first about pure substances. Here we are. Pure substances will always have a fixed composition. This means that no matter what you have in front of you, like a bowl of sugar, or if you had a mountain of sugar, or if you had a grain of sugar, that no matter the grain, the spoonful, or the mountain of sugar, each part of whatever you had would have exactly the same composition. Sugar happens to be made of carbon and hydrogen and oxygen, which are three elements in a particular combination. And no matter what sample size you have, it will always have the exact same proportions of carbon and hydrogen and oxygen that make up that sugar. This is what it means to be a pure substance. If it's just an element like carbon, then all carbon would be exactly the same at that point. So again, a pure substance. Pure substances could be elements, and there are 118 known elements that are found on the periodic table. 118 elements, however, actually breaks down into about 90 that are naturally occurring, that nature actually makes. The remainder are what we call synthesized elements, and they are elements that are made in the lab by people. Pure substance, however, can also be compounds, and compounds are simply chemical combinations of the elements, where elements have combined together, forming a chemical bond, kind of like a glue that holds them together. But the chemical bond is much more than glue. That's just a simple analogy. The chemical bond really changes the nature of those elements and creates a brand new substance. So sugar has nothing to do with carbon and hydrogen and oxygen that make it up. It's really its own unique substance. Here is a periodic table of the elements. This is a relatively up-to-date periodic table. What I notice is all the way down here in the corner, if I look, these last few elements have been actually filled in. In many periodic tables that are now out of date, these elements will have either no boxes at all, or there would be boxes with just made up names until that. But anyway, all of these elements have been officially recognized by the governing body of chemistry, if you will. Okay, let's talk first about elements. Elements would be any substance that is made of only one type of atom. And so no matter what you have in front of you, if it has only one kind of atom, it would be called an element. This is the simplest form of matter. It's what everything out there is actually made of. So some examples of elements, and of course we just had 118 of them, but examples would be like copper, gold, carbon, oxygen, very, very familiar names, very familiar substances, lead, neon. Al is a symbol for aluminum. Aluminum is a very good reflector of heat. W, which comes from a different language, Wolfram, I think it's German if I remember my languages, is actually what we call tungsten. And tungsten has a very high melting point. MP is melting point in this particular presentation. And then Ti stands for titanium. And titanium is a very, very strong metal. All of these would be examples of elements. Remember that, as I said before, there are over 90 naturally occurring elements, and the rest that we make, we call them synthetic. This would be a sample of unrefined copper. We can then, of course, process it, refine it, and make copper as a metal that we can then use in building and all kinds of different applications. This is unrefined gold, which of course we can refine and we can make jewelry or coins out of gold. This would be a sample of carbon, almost like what you would call a chunk of charcoal. And nature can actually compress this type of carbon and make diamonds, one of the hardest known natural substances. This would be a sample of, I believe, lead, which we could then make into various types of metals. And this would be representing neon, the gas. Now, of course, neon does not have all of these colors. It only has one color when it glows. But neon, like other gases, when it does glow, glows very brightly. We can then color the tubes to make these variations. Atoms. Atoms are the simplest form of all elements. And so if you take an element of copper, what is the smallest unit of copper? Well, that would be the atom of copper. And atoms of copper would have all of the properties of the element we call copper. Here again is a periodic table of all of the elements. It begins up here in the left with hydrogen. Hydrogen is the simplest known element in the universe. And unless we talk very exotic dark matter, which is a very interesting discussion, that all of the matter that we see in the universe, almost all of it is actually made of hydrogen, which is the simplest, and it kind of makes sense that the simplest element would be the most prevalent. After that, if we move all the way over to here, we have helium. Helium is what we call a noble gas. All of the elements underneath helium are also called noble gases, like neon. We were just talking about neon a moment ago. And then it continues to lithium and beryllium and what do we have? Boron, carbon, nitrogen, oxygen, fluorine, neon, and it goes on and on. Many of these names are very familiar. These are all elements, of course. Compounds. When we take elements and we chemically combine them together, we can make compounds. And compounds are very different from the elements that make them up. Very similar to a lot of things that you cook. Things that you cook are, when you're done cooking them and you eat them, are nothing like the ingredients that you actually put into it. So for instance, water, H2O. Hydrogen. Hydrogen is an explosive gas. Oxygen supports flame, but when you put them together, you get water, which actually puts out many types of fires. Sodium chloride, NaCl, is what we call table salt. Sodium is an explosive metal. Chlorine is a deadly gas. You put them together, and all of a sudden we have something we can put on our French fries. Calcium chloride is simply a different type of salt. And calcium chloride is most often the type of salt that we use to melt ice on our sidewalk, sometimes called ice melt. And then we have a compound called calcium carbonate. This CO3 unit down here, which is a carbon and 3 oxygens put together, has a special name that we call carbonate. But you put that together with calcium and you get what we call chalk, like sidewalk chalk, or the old-fashioned, if we had a chalkboard in the front of the room and we wrote on it with chalk. So this would be a representation of a crystal of salt. And this is, of course, what salt would look like if you found it just all chunked up on the side of a rock. Of course, chalk, most of us have played around with sidewalk chalk before, and this is where it comes from before they actually process it and make it into these wonderful little sticks that write on sidewalk. Okay, molecules. Molecules are the smallest part of a compound, very much like elements are the smallest part. Excuse me, let me say that one more time. Atoms are the smallest part of elements. Molecules are the smallest parts of compounds. Just like atoms and elements, molecules will have the properties of the compound. Two or more atoms chemically bonded together is what we call a molecule. This animation here, this would be representing a water molecule, actually, where water, H2O, these two, this thing looks like a Mickey Mouse to me, actually. So the two ears would actually be representing hydrogen, and this middle section would be the oxygen, so H2O for water. This next animation here that bounces in, this actually would be a representation of sulfuric acid. where the center is the sulfur here, this very large atom in the middle. That is surrounded by these four elements here, which are oxygens, very much colored like this, and then two hydrogens on the outside, one on either end. So H2SO4 is the formula for sulfuric acid. So elements and compounds. Let's consider the element sodium. Sodium has the symbol Na. It comes from the Latin natrium, is where the Na comes from. It's a silver metal, so if you find it, it's a silver metal. If you were to heat it up, it would actually melt before water boiled. I think it melts at 98 degrees Celsius, where water boils at 100 degrees Celsius. If you were to take sodium and put it in water, it practically explodes. It is so reactive. It does not like water at all, if I might say that. Consider chlorine. Chlorine is another metal, is another element. Chlorine is actually a nonmetal, the opposite of what sodium is. And chlorine is already a gas at room temperature. In fact, it's a poisonous green gas that was actually used as a biological, or I guess it was a chemical weapon in World War I. One of the first unfortunate uses of a chemical in warfare. And it's a very deadly green gas. You put these things together, and actually they would explode. They are very reactive together. They would explode. But the residue from this explosion would be a white powder. If you were to purify this to the point of where you could actually taste it, it would actually taste like salt, because you know what? It is salt. And we would then be able to refine it and put it on our French fries. So, sodium chloride, NaCl, it's table salt, and it's not anything like the sodium or the chlorine that actually make it up. Here is just a flask, or a jar, I guess, that is actually showing sodium and chlorine in the process of reacting together. When they are all done, the white residue that would be found in this particular jar would be table salt. Now, at this point, if you're just watching the regular slide presentation without narration, there would be a video that would either you'd click to play it or it would automatically play from this guy called Professor Dave. And Professor Dave, he has a lot of really good videos on science. This one only runs a little over 4 minutes. Here again, the link for this video, because it won't play now, is found on that Google Doc. So if you go back to the classroom, or if you go over to the Google Drive, remember we're chapter 18, that you will find the link for this particular video in that Google Doc. Okay, mixtures. Let's talk about then physical mixtures. Mixtures are simply physical combinations of matter. When you take two or more types of matter and you put them together, it's just a physical mixture is all it is. All the parts of a mixture, because they were physically put together, you can physically separate them. For instance, if you take salt, you put it in water, you stir it, the water dissolves the salt. You want to get the salt back out of the water, it's actually not all that hard. You could just evaporate the water away and the salt would stay behind. It would actually stay in the glass that you put it in. Every part of a mixture will keep its own properties, and that's why salt water will taste salty, because the salt does not chemically change. It stays salt. It's just invisible to the eye because the pieces have been broken up so much by the water that they're just so small to be invisible. But they're still salt, and water is still water, so it's just a physical mixture. This would be a chunk of granite. We've talked about granite before because we've talked about rocks and the rock cycle and earth systems and everything else. This is a physical mixture. All of these little bits of coloration showing you that it is a mixture. These are all different types of minerals that are embedded in this chunk of rock we call granite, which is, by the way, an igneous rock made from volcanoes. So this is cooled magma right here. And if we look at each one of these bits of color and we were to chemically analyze it, they would be just completely separate from each other. They all retain their own properties. So it's just a physical mixture, even though it looks complicated. Okay, so mixtures can be actually subdivided into two categories. One category is heterogeneous mixtures, like a bowl of Captain Crunch, one of my favorite cereals. Parts of a mixture would be easily determined. So anytime you look at a mixture and go, oh, that's a mixture, you're looking at a heterogeneous mixture. They're very, very easy to identify. A bowl of onion soup, bowl of Captain Crunch, Pepper, if you actually shake pepper out on your mashed potatoes. Pepper, you look at it closely enough, you realize it's all kinds of things that make up your pepper. Most everybody somewhere in their house has a junk drawer, or you have a jar where you throw every nut, bolt, screw, washer, nail, all these miscellaneous things. All of these are heterogeneous mixtures because you look at it and you know it's made of a bunch of different things. And sometimes not so obvious would be like a polyester shirt. It's a blend where it's 90% cotton, which is a natural material, and then a synthetic material, which is called polyester. And polyester with the 90-10 mix is then a heterogeneous mixture. Under a microscope, you could actually tell the polyester from the cotton in the weave of the shirt. Homogeneous mixtures. Homogeneous mixtures would be something like a bottle of Sprite, where it's a mixture. It is a physical mixture where the sugar and the flavoring that go into Sprite that make it Sprite are all in there, and you can taste them. However, you cannot see them. And so this is where two or more substances are blended so evenly that you actually cannot tell that they are a mixture without further testing. So some examples of homogeneous mixtures are Sprite, of course, salt water. If you dissolve salt in water and you had a glass of regular water and salt water side by side, you would not be able to tell until you tasted one or the other or both. Vinegar, you can't tell that it's vinegar. I mean, you certainly can smell it if you get close enough, but just by looking at it, it looks like clear water. Air is actually also a homogeneous mixture. It's a mixture of nitrogen and oxygen, as we learned when we talked about the atmosphere. And there's some other trace gases, but it's invisible, and we can't tell that it's a mixture. Gasoline, stuff that we put in our cars, is a mixture of all kinds of different types of fuels, primarily octane, which is the number on the pump when you go to pump your gas, and it says it's 85 or 87, 89, 90, 91, 93, and sometimes I've even seen 95. That's the octane rating. It's how much by percentage octane is in the fuel, which is really what makes your car go, go, go. But the other part is, because it all adds up to 100%, is roughly heptane and some other fuels that fill in the gasoline. And a solid homogeneous mixture would be like bronze metal. Bronze is not an element. Bronze is actually a made metal where we take copper, which is an element, we mix it with tin, which is also an element, but we just mix them together. We melt them, we put them together in the same container, we swirl them around to mix them evenly, and then we cool it down, let it solidify, and then voila, we've got bronze. Solutions and colloids. Okay, so solutions are actually homogeneous mixtures. And so the particles are so small they'll never settle out. Sprite is a solution, vinegar is a solution, salt water is a solution. A lot of things we use in chemistry are actually solutions. Whereas colloids are a different thing altogether. Colloids are mixtures, but they are heterogeneous mixtures. And they have particles that are so large that they won't settle out, but they're not large enough to actually be seen. Things like mayonnaise, shaving cream, toothpaste, fog are all examples of colloids. Colloids can appear cloudier than solutions when in a bright light. If we do shine a bright light into a colloid, now this doesn't work if it's something like mayonnaise, which is opaque, where it will not allow light to transfer through it. Shaving cream and toothpaste are also opaque, but fog is not. Actually, fog, you can see through fog. Even when it's pretty thick, you can see through it to a point. But a lot of these things can actually scatter light, and when they scatter light, some examples. Some examples of the Tyndall effect would be something like sunlight coming through dust on a road. So, we see the dust coming through the sunlight coming down through the trees, and we see the beams of sunlight. And the only reason why we see the beams of sunlight is because of dust and other particles in the air. If this is early in the morning, maybe this could be a little bit of residue fog, if you will. But this is the Tyndall effect, and most everybody has seen this before. Or light coming through a window, and you see the beams of light coming through a window. There again, it's because probably dust. Also, if you shine a very strong light through something like clear gelatin, you'll actually see where there's the beam of the light will be seen just like it is up here through the air. You can see the beam of light as it passes through this substance. This would be a colloid. Whereas a beam of light, you cannot really see it as it passes through a solution. There's nothing to scatter the light. But here the particles are large enough to where they actually scatter the light and you can see the beam. Here is a different example here, same idea. Here's the colloid. This would, without the light, appear relatively clear, but when you shine a strong light through it, the particles actually spread the light out. We see the beam. It looks cloudy. The solution does not look cloudy at all. The particles are too small to spread out light. Suspension. Suspension is also a heterogeneous mixture, and we all have had experience with suspensions, primarily something like a mud puddle or Italian salad dressing. So suspensions, heterogeneous mixtures, particles are large enough now to settle out upon standing, something like, so well, there you go, mud puddle and Italian salad dressing. You can make these things temporarily mix up by shaking them, or if you step in a mud puddle, it goes cloudy again. But if you leave it alone, the mud puddle goes clear as the dust and the mud settle to the bottom. With Italian salad dressing, the oil, if you leave it alone, will rise to the top. The water and the seasonings and the vinegar, which kind of give Italian salad dressing its flavor, all of those settle to the bottom, very much like in this example here, oil rising to the top and all the good stuff to the bottom. If you don't shake this up, all you're going to pour out is oil, and unless you really like the flavor of oil, it's probably not going to be all that appealing. But that would be a suspension. Okay, so we are done with section 1. Did you understand it? Do you understand the big idea? Matters classified by ... question mark. Can you define a substance and a mixture? Can you identify elements and compounds, tell how they are alike and tell how they are different? So compare and contrast. And can you compare and contrast these other types of mixtures, solutions and colloids and suspensions, heterogeneous, homogeneous? Can you also talk about those?